Running LLMs can be memory intensive and slow. Today, we will be exploring the game-changing benefits of AI quantization as a solution to these challenges. You will find out about the state-of-the-art techniques developed by Qualcomm AI Research, as well as the tools that we are open sourcing for developers. The webinar today is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Armina Stepan. I am with the tech marketing team here at Qualcomm Technologies, and I will be the moderator today. Before we get started, I would like to show you how this webinar platform works. At the bottom of your screen, you are going to see multiple application widgets you can use, including a widget to download today's presentation. All these widgets are resizable and movable. The slides will advance automatically throughout the event, and at this time, we recommend that you disable your computer's pop-up blockers. This allows the slides to advance automatically throughout the event. You can participate in our Q&A session by asking questions at any time during this webinar, and we will be answering them after the presentation. You just click the submit button, and then the questions come through to us. Also, if you're experiencing any technical issues, please type your question into the Q&A widget, and we will be glad to help. I would like to now introduce our presenters for today. They are Mart van Baalen, Senior Staff Engineer and Manager at Qualcomm AI Research, and Abhijit Kobre, Director of Technology at Qualcomm Technologies. Mart, please take it away.
Thank you, Armina. And welcome everyone to this webinar on quantization, unlocking scalability for large language models. Generative AI models such as ChatGPT and Stable Diffusion are disrupting traditional technologies from search and content creation to automation and problem solving. And they are fundamentally shaping the future user interfaces to computer devices. As generative AI adoption grows at record-setting speeds and computing demands increase, on-device and hybrid AI processing are more important than ever. And just like traditional computing evolved from mainframes to today's mix of cloud and edge devices, AI processing will be distributed between them for AI to scale and reach its full potential. In this talk, I, together with my colleague Abhijit, will cover what's next on in-device generative AI and what Qualcomm's role is in making on-device generative AI possible. So what we will talk about in this presentation is first, the importance of model efficiency, why we need it in this era of very large models. Large language model quantization motivations and challenges, why we need specifically quantization to enable LLMs to run on our devices, and what are the challenges that we face when we try to apply this. Abhi will talk about the software stack that Qualcomm has for this, so the way you can shrink models with the AI Model Efficiency Toolkit, or AMET, and the Qualcomm AI Hub. We will dive deep into a technique that we recently developed at Qualcomm that applies vector quantization to large language models. And at the end, we will give you, the audience, a chance to ask us some questions. Generative AI models create new and original content like text, images, video, audio, or other data. Generative AI is doing amazing things. I'm sure you've all seen Stable Diffusion and ChatGPT in the past few years. Large language models are a type of generative AI model developed for complex natural language processing tasks, capable of understanding and generating human-like text. They are trained on vast amounts of text data, learning language patterns which they use to create and contextually appropriate sentences. For text generation, ChatGPT has taken the world by storm. Originally based on GPT-3, which is a natural language model with 175 billion parameters, this evolved into GPT-4. A model with over 1 trillion parameters. And it kind of sounds like Dr. Evil when I say that. In May, OpenAI announced GPT-4o, which is a multimodal transformer and is more efficient than its predecessor. I would like to note that GPT is short for Generative Pre-trained Transformer, just to get that abbreviation out of the way. For code generation, GPT-3 and GPT-4 can also be used. So they cannot just generate text, but they can also perform other tasks, code generation, writing software. OpenAI Codex is an artificial intelligence model developed by OpenAI, which parses natural language and generates code in response. So as an example, you could tell it to generate a function that gives you the nth Fibonacci number, and it will spit out a function that does just that. It's used to power GitHub Copilot, which is a programming auto-completion tool developed for select IDEs like Visual Studio and Yovi. And I would also like to mention that there are newer, smaller LLMs that can also hold their own, such as Llama, the Llama family of models. We're now up to version 3 from Meta, which is an open source LLM, and Command R+, which is optimized for conversational interaction. It sits at just 35 billion parameters. So what does the generative AI ecosystem look like? We're now on the cusp of seeing a variety of new enterprise and consumer use cases emerge from generative AI, delivering capabilities that we have yet to even imagine. Foundation models, such as general purpose large language models, like GPT-4 and Lambda, have achieved unprecedented levels of language understanding, generation capabilities, and world knowledge. Most of these models are quite large, with more than 100 billion parameters, and expose their functionality to customers via APIs, because it's not really feasible to run those locally often. Access to these foundation models is leading to a deluge of both startups and large organizations building apps across text, image, video, 3D, speech, and audio. Examples of this include the code generation that we mentioned before, text generation, conversational chatbots, etc. But there's a parallel track as well, which is shown here on the right in this slide. And these assistant apps, which run locally on models and don't require API access. Instead, these are vertically built and include a smaller language model, which is run locally on a device, and which is the main topic of this talk here. So as the name suggests, these language models are very, very large, and we've mentioned this in the previous slide as well, but I would like to show you this graph to show just how quickly these models are growing. They're currently growing at an exponential rate. So if we look at state-of-the-art models in late 2018 and early 2019, for example, BERT Large or GPT-2, these models were around 1 billion parameters. But a year later, we see that GPT-3 has increased in size by 2 orders of magnitude to 175 billion parameters. And a few years later, we see that GPT-4 is again a full order of magnitude larger than these previous models. So these models are enormous. And this ever-increasing size of LLMs does introduce a few challenges when we want to run these models on device. First, LLMs being large obviously also require a lot of memory. Low-power edge devices have less working memory than cloud inference engines, which are used for example, GPT-4. So on these devices, LLMs need to share this memory with the OS and other applications as well. So there's a lot of pressure on DRAM when we run these memories. So these large language models, running them on device does create memory issues. Secondly, LLM token generation workloads look different than other deep learning workloads, for example, ConvNets. Token generation workloads require less compute per weight, and as a result, latency is memory transfer dominated rather than compute dominated. So latency is solved in a different way for LLMs. And in this presentation, we will talk about how quantization can solve for this. Qualcomm puts a lot of effort into its AI model efficiency research for improved performance of neural networks. This is what's going to allow inference AI to truly scale. Qualcomm is taking a holistic approach for model efficiency research, since there are multiple vectors to shrink AI models and efficiently run them on hardware. We have research efforts in quantization, conditional compute, speculative decoding, and compilation, as well as a few other topics that we won't get into in this presentation. These techniques can be complementary, which is why it is important to attack the model efficiency challenge from multiple angles. For this presentation, we will focus on quantization, as this is one of the most impactful techniques out there for reducing the size of your network. I would like to say that quantization is the best way to optimize your networks, and it's relatively easy and cheap to do. Furthermore, we will introduce a novel application of vector quantization to LLMs that further reduces network size, while still maintaining good accuracy. Our quantization research is about improving efficiency and performance. Quantization reduces the precision of weight parameters and activation node computations. To think of it in terms of an analogy, an image is comprised of RGB pixels. So if we were to quantize an image, we would represent each pixel with fewer bits. And if we go down to 1 bit, then this would essentially be a black and white image. For our AI models, quantization changes values not just from floating point to integer, but also from 32-bit to a lower bit width, like 8-bit. And quantization has great benefits. It reduces model size, but it also has positive effects on power efficiency and compute latency. So for example, if we have a FP16, 16-bit floating point model, which is the standard bit width for a lot of LLMs, we have an FP16 model and we quantize this to 4 bits, then this means that we reduce the model size by 4x. And based on how power is consumed in silicon, by using 4-bit integers in 4 rather than FP16, we see an up to 4x increase in performance per watt and a 4x decrease in memory bandwidth, both of which equate to a lot of power savings. We also achieve virtually the same accuracy between quantized int8 and FP32 AI model. In the next slides, I will be going deeper into the difference between floating point and integer quantization. Our quantization research focuses on shrinking model size to reduce latency and memory footprint, with additional benefits in power. Unfortunately, the benefits of quantization are not free. By reducing the number of bits used to represent the weights and activations, we change them a little bit, and this introduces noise into the model. So we call this noise quantization noise, and this quantization noise can have detrimental effect on model accuracy. A core challenge in quantization is therefore maintaining the accuracy of the original floating point models. So this is, I would say, the main challenge in quantization research. There's a related challenge in that the quantization bit width required for a deployment scenario may not yield sufficient accuracy for a task, which means that we need to look at more advanced quantization methods. And lastly, for some scenarios, the original training pipeline may not even be available, which would preclude these effective advanced quantization methods. Many methods have been developed in the last few years by both Qualcomm AI Research and other research labs that mitigate the harmful effects of quantization noise. Generally, we distinguish between two classes of quantization methods. Post-training quantization methods take a pre-trained floating point model and convert it directly into a fixed point network. And PTQ methods, post-training quantization methods, may provide cheap optimizations using no data or small amounts of publicly available data to mitigate the harmful effects of quantization noise. These methods usually require only limited to no quantization knowledge on the side of the end user, and they run very fast. In the case where the training pipeline of the floating point model is available, quantization network training, or QAT methods, train or fine-tune a network end-to-end with simulated quantization operations in place. This allows the model to adapt to quantization noise and restore accuracy. These models require more data, compute, and specialized knowledge on the side of the user, and are generally more challenging to use. But QAT does achieve the highest accuracy, especially at low bit width. For smaller models, QAT is an expensive but feasible approach to maintain accuracy at small model footprints. However, for LLMs, the cost of traditional QAT approaches becomes prohibitive. So while we're still actively investigating how to mitigate this, post-training techniques have become more important in the LLM era. Over the years, we have developed many novel methods to attack quantization noise, and I'm excited to see the speed at which research is moving to product or being open sourced. Our leading quantization research is being quickly commercialized and shared with the community through papers and open sourcing. We are truly driving the industry toward low bit with integer inference and power efficient AI by integrating our research into our AI model efficiency toolkit, or AMET. We recently put work on archive on low rank QAT for LLMs, which introduces a technique for more efficient QAT that significantly reduces the memory required for LLMs. Our latest work, GPT-VQ, which we will discuss in more detail in a bit, is planned to be integrated in AMET as well. And in the next slides, Abi will discuss how Qualcomm's quantization tools can be used by developers. So, Abi, you're up.
Thank you, Mart. So I'm going to talk to you about some of the tools we have for quantization for running models efficiently on the Qualcomm targets. So this slide shows you a picture of what the Qualcomm AI stack looks like. I'm going to start from the top. You have your frameworks like TensorFlow, PyTorch, where you have your models, or Onyx or Keras. Given these frameworks, you can apply different tools that we provide, like AMET, that we're going to talk about a little bit more. Or you could take it through various delegate paths like TF-Lite or Onyx Runtime. And then everything interfaces through a single interface called the Qualcomm AI Engine Direct into multiple accelerators on the Snapdragon platform, like the CPU, the GPU, the Adreno GPU, or the NPU. And there's a bunch of operating systems and drivers and so on to make all this work. So to make LLMs, optimized for targets, and our intent is to run these models completely on target, completely on device. We did a lot of optimizations across different layers of the stack. So we call this full stack optimization. And these allow us to run these models on target with very good latency and very good power consumption and with really good accuracy. So starting from the top, there are optimizations that are happening at a system level, like through architectural improvements, and we'll see an example of this coming up. There's model efficiency, where we apply different quantization optimization techniques to get good accuracy of these models. There are optimizations happening at a runtime level, at a compilation level, to run these models very, very efficiently on target with good power and reduced memory. And then, of course, all of this runs on top of the excellent AI accelerators that are built into the Qualcomm architecture, like the Hexagon NPU. So I'm going to talk a little bit about AMET, or which stands for AI Model Efficiency Toolkit. So this is a toolkit that allows models like TensorFlow PyTorch models to be optimized for quantized runtimes. So you take models from TensorFlow PyTorch, apply different techniques from the AMET, and you would get an optimized model, which is shrunk, quantized, and that could be deployed on different targets. AMET is an open source project. You can follow the link at the bottom and follow our development over there and contribute as well. So what AMET has, Mart talked to you about all the benefits of quantization, but AMET has a bunch of techniques, both post-training and quantization-aware training-based techniques. I'm going to talk to you in detail about a couple techniques, one on the post-training side called sequential MSE, and one on the quantization-aware training side called QAT with knowledge distillation, coming up soon. And there are new techniques we are adding specifically for LLMs in the near future, one on blockwise quantization and on vector quantization, which is what Mart is going to go in more detail. Here's a demo we wanted to show you. So we don't have the video running just in the slide due to some technical difficulties, but we'll post demo links, video links to you. So here's a demo that we did at the end of last year. It's a stable diffusion demo. So it's a text to image. You type in a text prompt at the top, and you get a 512 by 512 image generated. It's very fast. It runs in 0.6 seconds, a little bit under that. And there were several things that went in. So one of the things that went in is there is a efficient unit architecture developed for this with guidance conditioning and step distillation. And we optimized all of this using AMET and also all the runtime optimizations that we talked about before. And all of this was demonstrated running on a device, a phone device. We also recently demonstrated a demo on large multimodal models. So in a multimodal model, you may, for example, in this particular demo, also running on a phone, you could take a picture and ask questions about the picture to the model, and you can do multi-turn conversations about it. So in this picture, for example, you took a picture of something on your plate, for example, and you could say, hey, here are some ingredients. What can you make out of that? What are these ingredients? Can you make a recipe out of it? And you can do multi-turn conversations like this. The conversations, because the model being very optimized, they go at real-time speed. So you can do like a very natural conversation with it. Yeah, so this was, I believe, the world's first LLM model demonstrated on an Android phone. So let me talk to you about a couple techniques. So one of the techniques we've used for these models, both on the LLM side and the LMM side, the large multimodal models, is a technique called sequential MSE, or sequential mean squared error. And this technique works at it's a post-training quantization technique. It works at a layer by layer basis. So you apply it sequentially to layers, and then you apply it to the next layer and the next layer after that. And the technique works essentially to choose appropriate scales, quantization scales at every layer for the weights of that layer. And the scales are chosen to on the basis of looking at the loss compared to a reference model at the output of that layer. So as you go layer by layer, you start minimizing or choosing the scales to minimize the loss for that layer. And then you go to the next layer and next layer and so on and so forth. With this technique, we see that we see a good bump in accuracy. So if you take a look at these numbers, there are perplexity numbers for, this is a Llama V2 chat model with a 2K context length. And if we do just per channel quantization on this model, you may have a perplexity of something around 9.7. But if you apply sequential MSE, you can get like a good boost with W4 weights or 4-bit weights. You can get a perplexity of 7.83, which is very close to the initial. And if you look at LM eval or benchmarks, downstream benchmarks, you can see that the sequential MSE score comes close. So here, higher numbers, the better. And there's a delta about more than 2% here. But we can combine this technique with more techniques, like technique on knowledge distillation with QAT. So what is knowledge distillation? Knowledge distillation involves having a teacher model, which is generally a larger teacher model, teach a smaller student model on what it's, whatever it is trained to do. So what we do, while this is a standard knowledge distillation technique, we can combine this to do QAT. So here we used a Llama 2 chat 7 billion. So this is not a bigger model, if you may. It's the same size in terms of parameters, but the teacher here is running floating point 16, and the student is running an int4 model, again Llama 2 chat 7 billion. And there are two loss terms that get added up here. So one loss term corresponds to this knowledge distillation loss, or this divergence loss between the teacher and the student. And we also combine it with a regular training, like a cross entropy loss for the training. And by combining these two, we saw very good accuracy and very good characteristics in terms of convergence and quick convergence. So here's some numbers. So while there are a bunch of numbers here, I'll like to focus your attention on the first column. So the perplexity that we started on this floating point 16 teacher was about 7.9. The middle row is showing the techniques that we can, once we apply post-training quantization techniques, where we end up, and we ended up at 9.07. But if you apply knowledge distillation, you can actually get like within like 0.5% difference of perplexity. And if you look at all the remaining columns are essentially different common sense reasoning benchmarks, but pay your attention to the last column, which is an average of over these benchmarks. And you can see that with knowledge distillation and with QAT-KD, we can get to within 1% of this, which is a very good score. If with post-training, we were just over 2%. So we were able to reduce it down to 1%. And in practice, by looking at all these demos, the difference is imperceptible. I would also like to show you a new tool that we have introduced in the last few months called the Qualcomm AI Hub. And this is a very interesting tool. It allows you to deploy models on real devices. So the hub has a collection of pre-optimized models, including generative AI models that are already ready for you. But you can also bring your own model, and there are recipes to show you how you bring your own model, and then once you have optimized the model, you can push it to the hub. The hub has more than 45 cloud hosted devices like phones and IoT devices and compute devices and so on. And you can deploy the model, so you can take your model, optimize it, deploy it, see it running, and get back a score. And all this can be done very quickly with very little code. So we are very excited about it. Please, you could go to that URL and try it out for yourself. So on this note, I would like to hand it over back to Mart, who's going to talk about vector quantization.
Thank you, Abhi. So in Abhi's presentation, we saw that sequential MSE reaches very good results for post-training low bit-width quantization of large language models. However, even at 4 bits, LLMs are still very, very, very large. And we will now present novel work by Qualcomm AI Research on vector quantization and show how vector quantization can further shrink LLMs without harming accuracy. First, we will explain why vector quantization is a good method for low bit-width quantization. And to do so, we look at what happens when we quantize pairs of weights using different quantization methods. So this means that we have a weight tensor, and instead of quantizing each individual weight individually, we will quantize we will grab two consecutive weights out of this weight tensor and quantize them together. And in the plots on the slide, we quantize pairs of weights drawn from a distribution of values. The distribution of weights is represented by the blue blob in each plot. And this blob represents how often pairs of values occur. Darker colors, like here, mean pairs of weights with these values are more common, while the lighter colors at the edges indicate pairs of weights with these values are less common. So we have fewer weights here than pairs of weights here. And the 3 plots then show how pairs of values are quantized using different quantization methods. Each plot shows quantization to 3 bits per dimension. And since there are 2 dimensions in each plot, this is because we are quantizing pairs of values. This means that each value is quantized to 6 bits, or so this means that there are 64 unique pairs of values. The leftmost plot here shows quantization to uniform integer quantization. I should say that for this plot, we quantize each dimension individually. So this means that the first value in a pair of weights is quantized independently from the second value. And you can see that this yields a quantization grid that does not follow the underlying weight distribution well at all. In the second plot, we show quantization using one-dimensional non-uniform quantization. And again, this is applied independently to each dimension. And here you can see that it follows the marginal distribution of this blob better. But if you look at the joint distribution, so what happens when you quantize 2 values together, it is a bit better. It's a bit better than the uniform quantization case in 2D. You see that the quantization grid here is denser in areas where we have more weights. But it's clear that we can do better than independently quantizing each value in a pair. So if we look at the last plot, here we quantize pairs of values together. And this approach is called vector quantization, or VQ for short. And we can see that this approach follows the underlying distribution much more closely than quantizing each value in a pair independently. One thing to note is that for uniform quantization, we just store integer values. So we have a floating point value here, and then we quantize it, and this could be, at 3-bit, for example, this could be -3. Or -4, actually. But for non-uniform and vector quantization, we need a codebook. And this codebook is essentially a list of values. So for non-uniform quantization in one dimension here, we have a list of 8 values. And we would look up the closest value in the first dimension for this value and in the second dimension independently. And for VQ, in the 2D vector quantization case, we would have a list of values that a list of pairs of values. And in this case, our list would have 64 entries. So here's an example. If we have a weight that's in this area, it will be quantized to the closest weight, the closest pair of weights in this list, which could be, for example, this 217 pair that you see over here. And then what happens is that basically we can represent each pair of weights with one 6-bit index into this codebook. And if you have two 16-bit floating point weights that you start with, then this is obviously a big reduction in size. Let's now look at how well different quantization methods can represent weights in Llama v2 7b. And here we compare on signal to quantization noise ratio, or SQNR, between the original and the quantized weights. And we see that 2D vector quantization, which is this plot, actually performs a lot better than the 1D approaches. So here we have uniform quantization, which corresponds to this plot over here. We see that non-uniform quantization in 1D, which is this plot over here, performs better, but we do see a very strong increase when we go to 2D vector quantization. And what's interesting is that we see that increasing the quantization dimension, so this means instead of quantizing pairs of values at a time, quantizing 4 values at a time with a larger codebook as well, this yields even better quantization. You can see that here in this VQ4D plot. So in short, using the same number of bits to represent each individual weight, we can quantize the weights much more accurately using vector quantization in higher dimensions than traditional uniform quantization. And one thing to note about vector quantization is that it can actually be implemented efficiently on our hardware. So this is not just a cool academic result. This is something that we can actually apply, and I have some results on this later on in this presentation. But first, I will explain our method GPT-VQ, which is Qualcomm's method for quantizing LLMs using vector quantization. GPT-VQ is based on GPTQ, and this is a recent method for uniform quantization of LLMs. And this name is a pun that merges GPT for generative pre-trained transformer, which we talked about earlier. This is one of the most popular transformer architectures, with PTQ. If you can recall, this is post-training quantization. And the name GPT-VQ can be seen through the same lens. This is post-training vector quantization, VQ, for GPT-type models. GPT-VQ is an efficient method that iteratively quantizes groups of columns. So in this example, we focus on 2D vector quantization, where we quantize a pair of columns at a time. In this figure, green columns indicate weights that are already quantized, while gray columns indicate weights that are still in FP16 and so still need to be quantized. In each iteration of this algorithm, we select the first 2 unquantized columns. They're indicated here with these orange values. And each row in these columns is assigned to the most similar entry in the codebook. So this means that each pair of 16-bit values is just replaced by a single 6-bit index into the codebook. And this quantization step changes the weights a little bit, and it introduces noise in the weight tensor, which, as we talked about before, can cause issues. To absorb this noise, the remaining unquantized weights are modified using information from the input activations. And once we've done this, we move on to the next pair of columns. And we continue this process. We again update the FP16. We quantize this pair of values. We update the FP16 values until the whole tensor is quantized. And this method scales well. It takes between 30 minutes and 2 hours to quantize a 7 billion parameter model like Llama v2 7b or Llama v3 8b. And it takes about 12 hours to quantize a 70B parameter model. And this all works on a single H100 or A100 GPU. I mentioned before that VQ requires codebooks. And one thing to know about these codebooks is that to ensure representational power of VQ, as we increase the VQ dimension, the codebook must grow exponentially with VQ dimension. So for example, if we consider a toy example of 1-bit quantization per dimension, we see that in 1D, we have 2 values. But if we go to 2D, we need to store 2 to the power 2 or 4 values to ensure that we can still represent the same values as in 1D. Then if we go to 3D VQ, we need to store 2 to the power 3 or 8 values to keep the same representational power. And for 4D VQ, we need to store 2 to the power 4, et cetera, et cetera. So the more we increase the dimension, the more this codebook grows until we eventually hit the memory limit. To counteract the exponentially growing codebook sizes, we share larger codebooks over more weights. So for example, if a codebook doubles in size, this means that we double the number of weights that it's applied to. And this ensures that the overhead that we introduce from vector quantization stays constant. And this, in effect, means that we can compare vector quantization on an apples-to-apples basis to uniform quantization. And this is important because we don't want to make sure that our improvements on bit width per weight is purely because now we have this enormous overhead that we don't count. So yeah, and so we compare to uniform quantization where overhead comes in the form of an FP16 scale. We now show some weight-only quantization results of LLMs quantized using GPT-VQ and compare against state-of-the-art uniform quantization methods. We compare models in terms of perplexity, where lower is better on this side of the table, and on average over several zero-shot average scores, where higher is better. We compare results obtained with GPT-VQ to the original FP16 models, which you see here, and uniformly quantized models using state-of-the-art quantization methods, which you see in these rows. In each experiment, we choose an experimental setting for VQs such that fair comparison can be made with uniform quantization in terms of codebook overhead. So we make sure that the codebook overhead here matches the overhead that we get from the FP16 scale, and similarly for 3.125 bits per values. And we see that our GPT-VQ method achieves state-of-the-art quantization results at comparable bit widths. For the Wikitext2 perplexity benchmark, where lower is better, at 3.125 bits per value and two-dimensional vector quantization, we are close to the FP16 values in the top row in this plot, and better than all other uniform methods except for 4-bit quantization. Furthermore, if we look at zero-shot average accuracy, we see the same result. The 3.125 bits per value 2D results are better than the state-of-the-art quantization methods and better than all other methods. What's also interesting is that higher VQ dimensionality improves our results. So if you look at this 2D, 2-bit per dimension result in the top, we see that for 1D, if we go to 2D, we get better results. And then if we go to 4D, we get even better results. And the same thing holds for 3 bits per index results. And what's important to note is that other methods see much more significant degradation at 3 bits and a very significant degradation at 2-bit quantization. Lastly, GPT-VQ at 3.125 bits per values has results that are competitive with Int4 per channel quantized models. So this means that we can get accuracy that is comparable to Int4 with models that are about 20% smaller. In summary, we've seen that VQ can achieve the same accuracy as Int4 uniform quantization at about 20% smaller model size. But how well does it actually run on device? In this table, we compare 2 tasks, data transfer. So this means getting data from memory to the core and unpacking it. So for VQ, we need to do a lookup step to unpack the weights, but this is offset by the fact that we need to transfer less data to the core. So for uniform quantization, for example, we have as our baseline 4-bit quantization, whereas for our VQ results, we look at models that are quantized with 3 bits per values or even fewer bits per values. So this means that they use 25 to almost 50% less data to transfer, but we do need to do an extra step. So the question is, how does this affect latency? So we look at transfer. We also look at matrix vector multiplications. And matrix vector multiplication is the core operation, or the workhorse really, of LLM token generation. And here we integrate the data transfer with the matrix vector operation. And we see here that relative footprint is significantly reduced, releasing some of the pressure on DRAM from LLMs. But what's also interesting is that while we do have to do a bit of extra work to unpack our VQ models, we don't have any adverse effects on latency, and sometimes even significant reductions in latency, for example, for this experiment or this experiment. So in this presentation, we've seen that LLM quantization addresses the constraints of making AI work on device, solving memory and latency challenges. We've seen that vector quantization shrinks models while maintaining the desired accuracy and even sometimes getting benefits in latency. Qualcomm AI Research has achieved state-of-the-art results in quantizing large language models, and Abi has shown that the Qualcomm AI Hub provides useful tools for developers to quantize their own models. Thank you very much for attending this webinar. We have a list of channels through which you can stay up to date on the work being done at Qualcomm AI Research. And if you have any questions, then as Armina mentioned, please post them in the appropriate text box, or contact us through some of these other channels. Thank you very much.
Thank you very much, Mart and Abi. I see a lot of questions already coming in, and we'll sift through them as much as possible, and we'll try to follow up after the presentation if we don't get to all of the questions here. So just to start with one, I think, pretty important question, and that's mostly for Abi. How soon will we see blockwise quantization and vector quantization in AMET?
Yeah, good question, Armina. So we're working on this actively at this point. I would think in the next couple, 2 to 3 months, I think these techniques should be part of AMET.
All right. So we'll, I guess we'll just continue refreshing the Qualcomm AI Hub and GitHub and find out when it goes live, when they go live. All right, next question. This is for Mart. Is there a synergy between vector quantization, so VQ, and other quantization techniques?
I would say they're a bit independent. One thing we do need to keep in mind is that the codebook actually needs to be quantized. But once you have once you have the quantized codebook and you have the indices into the codebook, there's nothing else left to quantize really. So there's a synergy in the sense that we can quantize the codebook itself to different bit widths, and this would reduce the overhead a little bit. But other than that, I would say no. And maybe a nuance to this answer is that we can choose to have certain layers in uniform quantized bit widths, or that we can mix and match. We have a mixed precision approach already, but we can extend this to different quantization paradigms as well, for example. But you cannot apply, let's say, uniform quantization on top of vector quantization.
Okay. Clear. We've covered the advantages of quantization, right, when it comes to memory and latency. But a question that came up is, are there any disadvantages for the users or the user experience by hosting these models on device? And this is for both of you.
Any disadvantages for the user? I mean, if the model is run locally, it has benefits in terms of, but it also means that the battery and your core now has to run the model, which warms up the device, and it can drain the battery faster. And this is also why Qualcomm focuses so much on quantization, because going to lower bit widths will reduce these harmful effects. And also our hardware teams are very, very good at squeezing everything out of each individual watt in terms of compute.
Yeah, to add to that, yeah, there are a whole bunch of advantages to running models on the edge devices, right? So I think we should, maybe look from that angle. But running these models, these very large models on device with low precision does have accuracy challenges. I think, and whatever this presentation is showing is how we are counteracting those accuracy challenges with new techniques and new tools and so on and so forth. So yeah, there is lots of stuff to gain. Yeah, there are power challenges, but I think with the Qualcomm NPU, I think we are in a very good shape in terms of running these generative AI models on target with good power, which doesn't hurt battery life for devices.
Yeah.
Yeah. I did see actually a question that was directly about the NPU. So is DirectML support available for Qualcomm Snapdragon X NPU?
So That's a good question. I would maybe direct you to the AI Hub portal, and then you should be able to try. So there's work going on to enable lots of different paths into Snapdragon, and direct ML is one of those paths. But please visit the AI Hub and then follow up from there.
Yeah. Speaking of the trade-offs that you mentioned before in terms of dimensionality and memory limit, how high dimensional can you get with VQ without reaching the memory limit? This is for Mart.
Yeah, you can actually get quite high with this. I would say that a problem you would run into earlier is that the overhead of the codebook becomes so large that the benefits disappear. So I think you can get quite high with this. I would say maybe at 16 bits, you would start getting very large codebooks that become unwieldy, not just for the memory, but also for the the memory that's required during the optimization algorithm, and the overhead that it introduces. So even if you have a low bit per index, you would still have a very, very large codebook that you would need to store and transfer, mitigating any of the benefits that you get from vector quantization. And this is also why we focus mainly on 2D and 4D, because there we find a sweet spot between a fast algorithm, memory overhead that's low enough that the benefits still outweigh the downsides of the large codebook. And it's still feasible to implement efficiently on device as well, which is also a thing that becomes more challenging when you get to very large codebooks.
Yeah, indeed. So there, yeah. You spoke a little bit about post-training quantization, right? A question came in, I think is interesting, is are there any strategies for tuning model performance post-quantization? I think this may be an AMET-related question for Abi.
Yeah, excellent question. So in general, there are, there are a bunch of algos, bunch of techniques that you could apply post-training. But in practice, what happens is, like, for different architectures, like large language models being one kind of architecture, or large vision models being another kind of architecture, like diffusion models. For given an architecture, there is a recipe that generally works well. And what we try to do is we put this, we try to release this recipe as a guidance to the users through notebooks, either on the AMET GitHub, or also through the hub. So yeah, there are, like, for example, for large language models, if you are sticking to per channel quantization, we have these recipes of using the sequential MSE technique. And then if you really wanted to push it further, use the quantization aware training with knowledge distillation technique. But going later this year, we would change the recipe to recommend blockwise quantization, and then push, if you wanted to go lower bit width, push with vector quantization. So we can guide users through these recipes, and that's what we do. But the short answer is there is no one fits all technique that applies to all kinds of models. So it depends on model by model.
Yeah.
Okay.
Yeah. I had actually a curiosity on the blockwise quantization. Can you combine it with other techniques, like, for example, sequential MSE? Is there a benefit to it if you do that?
That's an excellent question. So yeah, blockwise quantization at its very core is basically is increasing the resolution of the quantization, essentially applying quantization with smaller blocks instead of full channels. And yeah, we can combine this technique with other techniques. And what we have seen, and we are doing, the research is still going on, but we are seeing benefits. So you may get to a particular accuracy just by applying blockwise quantization, which is very, very quick, very, very fast. But you can combine it, say, with sequential MSE and get a boost in accuracy. So we'll publish results as we go along onto the AMET GitHub, and you can follow along. But yeah, absolutely, you can combine the techniques.
Nice. I think that going back to the vector quantization technique that Mart presented, some of the attendees were wondering about where do small LLMs fall in this? Is there a motivation to also improve activation quantization on small LLMs? What are your thoughts on that?
What do you mean exactly with activation quantization in this?
So it says as follows: the GPT-VQ it applies to weights. The user asks, is there motivation to improve activation quantization for small LLMs, or is this just for big LLMs?
I think maybe the first thing to clarify is the GPT-VQ or VQ in general doesn't apply that well to activations, because to quantize an activation using VQ, you have to do a lookup on to what is the closest vector, and this is the closest entry in the codebook, let's say, and this is quite an expensive operation. So when we do it offline, it doesn't really matter because we do it once, and it's not that expensive if you do it once. But if you do it many times, like you need to do in activations, it becomes a pretty big latency bottleneck. In terms of small LLMs, yeah, I mean, the same benefits apply. For small LLMs, like with big LLMs, latency is dominated by weight transfer, because we still mainly have matrix vector multiplications as our workhorse, as the main thing. So this means that we still have very few multiplications per weight. So in this case, we would still have benefits from vector quantization over uniform quantization in terms of model size and in terms of data transfer speed and in terms of latency, potentially.
Right.
I would also like to add to that is, if you see large language models in general, I think the bottlenecks are in memory overhead. I think there's so much.
Yeah.
These models are so large, and both the amount of RAM that you have to use to store the weights, but also the memory bandwidth that is needed. So these models get very memory bound, and so I think attacking that's the bottleneck that we need to attack, and that's exactly what vector quant is attacking.
I think this also kind of falls in the category of bottleneck, but I'm not sure if you mentioned this. What is the computational cost for post-training a GPT model, a quantized GPT model, by utilizing the method that you propose?
The cost, I did mention. So in terms of, I can tell you the cost in terms of wall clock time. This is maybe the easiest to use. So if you run it on an H100, it takes about 30 minutes to 2 hours, depending on the specific setting that you use to quantize, to vector quantize a model using GPT-VQ. And this changes with, and this is a 7B size model, so Llama V2 7B, for example. If you go to larger models, of course, it will be slower. And this is mainly affected by the settings of vector quantization. So if you do one-dimensional, 2 bits per dimension vector quantization, the codebook will be very small, and it will be very easy to optimize. It will be very quick. On the other hand, if you go to 4-bit quantization at a high dimensionality, you get a very large codebook, and this will slow things down a bit. So then you're getting closer to the 2-hour range. And in terms of cost, so we're talking here about an H100 with 80 gigabytes of memory.
Mm-hmm.
And if you look at that same thing on target, essentially the overhead of running vector quantization is pretty minimal. So it has almost similar overhead to running per channel quantization, with a little extra overhead of some lookup that has to be done. But yeah, on target, I think the overheads are not great. Yeah. So you can get the benefits without having a lot of overhead.
Yeah.
All right.
So one very minor thing to add to that is that this lookup operation is actually supported in hardware. So this is not a thing. We've had this question before. We don't need to go to RAM if we see an index. We don't need to go back to RAM and and fetch the weight. But we can store the codebook. The codebooks are ultimately small enough to store them in register. and we can look them up with lookup table operations.
Clear.
But maybe that's a bit too.
The sequential MSC technique, I see there's some questions on this as well. So going back to Amit, actually a question for Abi. For int8 weights, should we use sequential MSC?
Yeah, you can. So I think essentially the benefits, depend on model to model. I think for 4-bit weights for LLMs, we've seen like quite a good boost there, as you saw from some of the results. With 8-bit weights, there may be, we'll have to see how much boost you get. So the boost may be a little more muted, but it should help nevertheless. So yeah, you can apply that technique irrespective of bit width. Yeah.
Sounds good. So int8 is a go for sequential MSC. An attendee is asking, where is the speed up coming from? Is it from less data movement or is it from less compute?
It's less data movement. It's a little bit more compute even, but it's less data movement, which offsets the compute. So this, yeah, I would say that that's the main thing.
Yeah, I mean, as we know that there is, some of these models are memory bound, but it's kind of an interesting problem because if you look at large language models, there is a prompt processing phase, if you may, meaning, let's say you give it a big prompt, and so first it has to like consume that whole prompt, and then there is a sort of a token generation phase. So I think it would maybe more memory bound in one case versus another. So essentially having a quantized, like 4-bit quantized models helps obviously on the memory side and the memory bandwidth side, but also like doing with 4 bits, you're doing essentially 4-bit weights multiplied by 16-bit integer activations. So this kind of multiplication is much more efficient, at least on Snapdragon hardware, compared to like floating point 16 kind of computation. So I think there is benefit to have both on compute and on memory.
All right. As we're approaching the end of this presentation, I would like to just round it off with one more question, and that is for both of you, or whichever feels inspired to answer. What is your prediction in terms of the rise of the small but powerful LLMs, and also how about other LLM trends that you're seeing?
I think for smaller LLMs, we've seen really interesting developments recently. So for the Llama family of models, they've stayed roughly the same size, but we've seen them increase in their capabilities with each release. So Llama v3 is worlds better than the original Llama release, and even in the Llama v2 one. And we've seen, for example, Microsoft's 5 family of models, which are also quite small, especially compared to the trillion parameter-sized models from OpenAI, but are very, very powerful. Some even getting close to GPT-4 level capabilities. And so I think that, the view I have is that these large language models, when we first started using them, they were super heavily over parameterized, and now we're figuring out with better training procedures, with better data mixes, how to get more out of much smaller models. So I think we're going to see an explosion of models that are in this 7 billion, 13 billion range, and which will be feasible to run on device using our techniques and a bunch of other techniques that we're still developing. So I think the future of that is quite exciting actually.
And if I have to add to that, I'll answer from a different angle. So if I look at use cases, I think the use cases of running, I believe generative AI is going to take over our world. There's so many, very, very interesting use cases coming along, and they'll just keep exploding. And if you really think about it, it just makes sense for these use cases to be run on the devices in your hand, whether it's your laptop, your phone, your car, so on and so forth, right? So this edge device, running models and generative AI models on the edge, I think is just going to keep exploding. And from that, if there is a use case, there will be a solution. So I think I can see, I'm very, very optimistic that there's going to be much more work on smaller models, I think, which run very, very efficiently on the edge. This is going to change our world.
Yes, we're looking forward to it. Thank you very much to Mart and Abi for this great presentation. On behalf of Qualcomm and the presenters, I would like to thank you all for joining us today. This webinar will be available on demand, as well as the resources that were mentioned throughout the presentation. I would like to wish you a great rest of your day.
Thank you, everyone.
Thank you, everyone.